So now everyone should see my screen. So hello everyone, I'm Laurenz, and I'm now working at a postdoc at Ghent University. But during my PhD, I tried to visualize biofilms inside stones, and I was faced with many problems with the X-ray attenuation contrasts, of which I will tell you more now. So the contrast is actually an obvious difference between two or more things, and it's basically necessary if you want to distinguish different objects from each other. And the contrast that we get is actually the result of the interaction of X-rays with matter. When X-rays passes through an object, their intensity will decrease because they get attenuated, and there will be a shift in the phase. The amount of attenuation is related to the density and the composition of the material. And it's this difference between two objects that will create the attenuation contrast. And if this difference is big enough, we'll be able to distinguish two objects from each other or to see two phases within one object. You can also have a phase contrast, which results from the difference in phase, but here we will mainly focus on the attenuation contrast. So when you have a sample which have very big differences in composition and density, you can easily see the different phases, as I've shown here in this example from Savoniera limestone. You can see here the stone, which has the brightest or the highest gray values as it absorbs most X-rays. You can see in dark here and here a gas phase, which almost absorbs no X-rays. So that's why it's very dark. And in between, you can see the water phase. So in this sample, it's quite straightforward. But I want to also point out that even here, there are already some complications. As you see, within the stone, there are different gray values, and this is not related to any kind of different composition or so. This is related to the partial volume effect, as they are micropores present, which also change the gray value a bit. So I want to address here that it's always important to have some prior knowledge about your sample. Although in many cases it's not easy or it's very hard to distinguish different phases from each other, as they have no X-ray attenuation contrast. There are many objects which have a similar composition and density, so they have the same or similar X-ray attenuation, and then also the same gray value in the reconstructed slices. Examples are, for example, are in soils, where it's very hard to distinguish, for example, organic matter from air, to see, for example, the difference between water and ice, but also it's hard to distinguish different minerals in one rock. And for this, I use this illustration where you have the attenuation of different minerals inside a granite over the range of energy you can work with your CT system. And as you can see, it will be very easy to distinguish, for example, magnetite with albite or quartz. But distinguishing albite from quartz, this will be very hard or probably impossible. What you also can see in this figure is that when you increase the energy of your X-ray source, the contrast decreases. So basically you can play already a bit with the energy to increase contrast, but you should always keep into account that you cannot reduce the energy too much, because otherwise you won't get enough signal anymore. So that's a way how to solve it, but there are also other ways. And for this, I will go back to my own research I did, where I try to visualize biofilms within the stone and to distinguish them from water. And based on that kind of example, I will explain the ways how you can treat with it, how you can deal with problems with phase contrast. So, but first, what are biofilms? Well, biofilms are like bacterial colonies, which also can contain other microorganisms that are embedded in extracellular polymeric substances. So basically, these are actually cells which are embedded in a kind of a slime. And this is 99%, this all consists for 99% out of water. So it's basically the same composition. They are created like when bacteria colonize a surface, they will group together and they will form big structures which should be able to see with microscopy because they're big enough, and you can also see them often on stones and on monuments as they induce discoloration. But why was I interested in them? Well, the reason was that they affect stones in multiple ways. When they colonize a surface, they will often mostly also colonize the pores. And when they do that, they will actually clog the pore space and they will change how water is transported in the stone. They will change the wettability, and they can, for example, retain water and change the drying regime. So they can have quite a big effect there. On the same hand, the biofilms or the bacteria there, they will often produce acids that can dissolve certain minerals, which can lead to weathering, or they can oxidize or reduce certain metals, which can lead to manganese stains, for example. On the other hand, they can precipitate minerals, which are often carbonates that can be used to seal cracks in, for example, concrete. If you want to study like the effects of dissolution and precipitation within a stone, microscopy is very straightforward to use. You can easily see where materials is lost or added. But to see like the link with the bacteria and to see how the bacteria affect water transport, it is necessary to distinguish them from water. And yeah, that's a bit tricky. So if you have bacteria which are growing in between sand grains, for example, which are here in green, you can see the water, you can see the sand grains. If you would make microscopy image from that, well, you will almost see nothing. Well, you will see the grains and you will see a phase in between, which is water and biofilm, but it's impossible to see the difference between the two. So what you can do is you can add a contrast agent which will allow to distinguish these similar phases, and it also allows to reveal light objects within dense materials such as stones. Because when you are looking, like for example, to biofilms in stones, to go with X-rays, to penetrate enough X-rays to the stone, you need a lot of energy. And this also makes it very hard to reveal light objects which have like a low density. So their contrast agents can be handful as well. Contrast agents are in general heavy compounds, and they can consist of everything. They can be liquid, they can be particles, and even gas. There are two types of contrast agents. The first one is like the positive contrast agents, which increase the attenuation of the surrounding phase. In this case, it would increase the attenuation of the water phase. A negative contrast agent, on the other hand, increase the attenuation of the phase or stains, let's say the stains the phase you're interested in. In our case, would make the biofilm visible. Positive contrast agents, they were often successful to visualize biofilms, and here I put the example of barium sulfate. What you can see on the left is a cross-section through a sand column in which bacteria grew. After bacteria were grown, I pushed out the water, let's say, and replaced them with a barium sulfate suspension. The barium sulfate is very dense, so it has very high attenuation, and you can see it like with the white phases on the picture, on the image. But the particles, they are too big to enter the biofilm. So the biofilm remains unstained. So now it's possible to distinguish the biofilm from the barium sulfate. It works quite well, but there are some problems related with this contrast agent, as these particles, they're very heavy, so they can sediment while you do the scanning, which can cause artifacts. When you push them through to replace the water with them, you can remove the biofilm as it creates a lot of stress or tensions or shear, and it's actually not proven that the particles do not enter the biofilm. But the most important downside of working with positive contrast agent is that you're not working with water anymore. So what I mean is you cannot, for example, now study how the biofilms affect water transport, because this barium sulfate solution is very far from water, let's say. Another example of a positive contrast agent is 1-chloronaphthalene. And that's actually a hydrophobic solution that does not enter the biofilm as well. And I show an example here. This is again a column or like a flow cell where grains in and where biofilms grew, and then the water surrounding is replaced by the 1-chloronaphthalene, which has a higher attenuation coefficient. So you can distinguish it now from the water. But also here the problems are with this specific one, it's very toxic, and actually also that's hydrophobic. So you cannot really say like if you're interested in how they affect water transport, you cannot study it with this because it's even hydrophobic. So what we can do is we can try to work with negative contrast agents that stay in the biofilm, because they do not affect the properties of your pore fluid, because when you grow your bacteria, you add the contrast agent, the contrast agents attached to the biofilm, and then you can just remove everything which was not attached. Although this is much more challenging, and there are a lot of factors that you should keep in mind. And the first one is you should take a contrast agent with a high enough atomic number, so it creates enough of attenuation or contrast. And this is something that you also have to look at when you are dealing with with positive contrast agents. But here you should also think about the concentration, and especially the concentration that is attached, that is absorbed by your phase of interest, or here the biofilms. The contrast agent should also remain absorbed, so it should not get detached when you remove the non-attached contrast agent. You should think about how long am I staining, and does it keep your phase of interest stable, and it should be evenly distributed. And this can be, so this accounts for all contrast agents, negative contrast agents, and it's sometimes hard to find the right balance between all these factors. And if you're like working like me with a living creature, you should always also think like, what do I want to keep the bacteria alive or not? And this will be very important because if you don't care that much, if they survive, then you can use higher concentration. Often it's okay to use higher concentration as long as the shape of the biofilm remain intact. So, but these contrast agents can work, and this is an example of a stone where a biofilm was grown on, which was stained and then submerged in a salt-rich solution. And as you can see now, it's, well, a salt-rich is a physiological solution, which is a PBS. And as you can see, there is an extra phase visible. You can distinguish the biofilm from the physiological solution, but the contrast agent I use is not ideal because it's not evenly distributed. You can see here, if you see my cursor, that there are zones in the biofilm where there's like higher attenuation because contrast agents was precipitated. What's also important to think about is that not every contrast agents give the same effects. And in my case, some contrast agents show my biofilm differently. And that's caused because the contrast agent does not necessarily bind to the same feature of the biofilm. And this was shown in this example where this is cyanobacteria, where I imaged cyanobacteria, which were covering a stone. These were stained with two contrast agents, A and B, which are like left and right. And what you can see is that on the left, you see much more detail compared to the contrast agents used on the right. And this is actually the same biofilm, so it shows that, they probably get attached to something different. So there's also something you should take into account. But it's interesting because it also means that it might be possible to use different contrast agents complementary to show different features you are interesting at of the same object. Besides contrast agents, there are also other possibilities to enhance the contrast. And one example is that we can also, so besides the attenuation, you can also look at the phase shift, because so like I said, like when an X-ray passes through an object, also the phase will change. And for certain materials, the change in phase will be much larger than the change in attenuation. So you can also exploit these changes to get more contrast. There are several ways to do this, and the easiest one, and the one that I also did during my research, is to increase the distance between the sample and the detector. There are also other more advanced ways, I would say. You can work with optical elements, or you can also use the gratings for the contrast, just also like Jan explained. But you can also in biofilm visualization, this was be used, and it can also, of course, be used in combination with contrast agent that we just saw. And I showed you an example here. Like this is again like a flow cell where there are sand grains or another kind of grains in which biofilms grew. As a contrast agent here, iron sulfate was used, of which the bacteria of the biofilm constantly oxidized, which led to precipitation and incorporating during growth the iron. The iron is not ideal because it's not that heavy, so it's still hard to see on the upper image like a lot of biofilm. However, when you use phase contrast by increasing the distance and some extra filtering, you can better see the different phases. And this is also shown by the curves you can see on the right, which show the gray values. And like the red one on the top, which is P2, here it's very hard to distinguish biofilm from the liquid, from surrounding water. But when you use a phase contrast, it becomes difference becomes much more visible. So it can be a valuable asset to try this as well if you're dealing with contrast issues. Another last way to do it is you can use dual energy, where you acquire an image based at two different energies, usually a high and a low one. This is because the linear attenuation coefficient of an element changes with the X-ray energy. This is a gradual process. This is gradual, except for there are some specific step changes at characteristic absorption edges. Using these edges, you can identify the presence of certain elements, but you can also enhance the contrast. This can be very helpful, but of course it's not helpful for biofilms, just like that, because the biofilm is basically water for 99%, so it will be very hard to distinguish something else with this technique, although you could use here also a contrast agent, which might be not sufficient to visualize the biofilm just like that. But with dual energy, you can maybe track down where that element of your contrast agent is sitting or absorbed, and then you can also visualize the biofilm. So these were the main methods how you can enhance contrast. Before I end, I will show you some other examples that you don't only think you can only do it with biofilm. And the first one I want to show is something I found in a paper from Nadiv, and he wanted to distinguish ice from air. So not water from air. So what they see is that if they before staining, if they don't stain, it was very hard with the setup to distinguish both phases. You can see here the sand grains, but in between you don't see any you don't see difference between the ice and the air. However, after you stain the ice, it becomes much more visible and it will be much easier to do any kind of analysis on the data. You also see it when you look at the grayscale images. You see when there's no contrast agent, there are only two peaks. The left peak is just from the air and the right peak is from the is from the grains. But when you add the contrast agent, there is also an extra peak coming in the middle, which is the ice. Another example, which is quite common in geology, is to distinguish organic matter in soils. Here, like on the left, you use no contrast agents, and as you see, it's very hard to distinguish the soil organic matter from the surrounding air. The other phases which are visible are the minerals and the glauconite. When you use a contrast agent, then you can increase the attenuation of the soil organic matter. And it becomes brighter, which is also visible on the gray, the attenuation graphs of the different phases of the gray, of like say the grayscale of the different of the image. Here's also important to take into account which contrast agents work best for your for what you're interested at, because you can increase the attenuation easily in this case of soil organic matter, but you have to make sure that it doesn't come too close to the gray value of the glauconite, otherwise you create other problems. The last example I want to show is actually not related to geology, but related to histology and medical science, because there the lack of contrast is a very big problem. And my advice is, if you have problems like in your field of it, and you really don't find any solution, if you look at geological papers, like how can I solve this, then go back to the medical science, because they have much more, let's say, also means to do research, and they have done a lot more research. Certainly when it's about contrast agent, because like when you have, I think this is a red, and like in A there's no contrast, you only see some tissue and some bone. But when you add different contrast agents, such as B, C, D, and E, you can see different features relating to which contrast agent you are using. For example, C will enhance the attenuation of the heart very much, while in B it might be very interesting for the kidneys, or in D also for the kidneys. So here it also shows that you can use a lot of contrast agents, and they all have different pros and cons. It's not always that easy. It all depends what you're interested in. And this is the end of my presentation, where I hope you remember that it's quite hard, sometimes hard, to visualize different phases as they have similar X-ray attenuation contrast. However, we can enhance the contrast by reducing the energy, but also by adding contrast agents to do phase contrast imaging, or even dual energy CT. That was my presentation. Thank you very much. If you have some questions, I would like to answer them.